Hello, everybody. I welcome you all to this month's Brown Bag webinar. We are very proud to have Julian Waltzberg and Rebecca Haynes from the National Renewable Energy Laboratory. Julian is NREL's Strategic Energy Analysis Center, SEAC, where he works on various circular economy projects. His postdoc research carried out within SEAC as well focused on applying agent-based modeling to analyze circular economy opportunities for various technologies. He's also an alumni of the Ellen MacArthur Foundation from Linear to Circular program. And Rebecca Haynes is an engineer in SEAC working in the broad field of sustainability-related decision support. She uses a wide range of modeling methodologies to represent large-scale industrial and agricultural systems and explore how those systems can meet humanity's material and energy needs while causing less harmful environmental and other impacts. After their presentation, we will have one of our analysts, Amos, take your questions and ask questions for you. So welcome, Julian and Rebecca. Please take it away.
Thank you, Holly. Welcome, everyone. Thank you for attending this presentation, which is about the circular economy lifecycle assessment and visualization framework, current and future capabilities and application. So just a little bit of background first before presenting the framework. You may be well acquainted with the concept of the circular economy, but a little bit of a reminder here. The objectives of the circular economy, or CE, is to optimize resource yields by circulating products, components, and material that are in use at their highest possible utility. It also aims at preserving and enhancing natural capital and foster system effectiveness by designing out negative externalities. In order to do that, the circular economy relies on four overarching principles: narrowing flows, so using less materials and products in the first place; slowing flows, using those materials and products for longer; using regenerating flows, so for instance, using renewable energy or biosource materials; and finally, cycle flows, so recycle materials or at least recover some energy from them at the end of life. So the objective of the CELAVI framework is to assess the type, quantity, and spatio-temporal distribution of impacts that may occur when a supply chain transitions from linearity toward circularity. And so the framework simulates a circularity transition within supply chains and quantifies the associated environmental and economic impact. So when we first started this project, we were looking for what type of methods could answer some of the requirements that are needed to model circularity transition. So for instance, some of those requirements being to incorporate uncertainty. Transition phenomenon are quite uncertain, so we need to account for that. We also need to represent regionally and temporally resolved environmental impacts. We wanted to look at the US and the US state or final resolution. And because, again, we're looking at transition, we need methods that can account for temporal aspects. So we need dynamics of transition to be modeled. And so we looked at different type of methodologies. You can see there on the table. And we found out that discrete event simulation, network modeling, and lifecycle impact assessment were three methods that could answer most of those requirements if they are combined together, which the CELAVI framework does. And so by combining those three different types of methods, we can also include three levels of technology resolution. So we can look at individual material. In the example of a wind turbine, we can look at cement from the foundation. We can also track other materials such as composites and so on. We can look at individual components. So for instance, wind blades, and we can look at the whole technology unit. So for instance, wind farms in the case of wind power. And for the details of the framework, I will hand it off to Rebecca.
All right, so I'm going to dive a little bit more into the technical details of our CELAVI framework and how it functions. This part of the presentation is structured around the three core modules of the framework: the discrete event simulation, or DES, the cost graph, and the Python lifecycle impact assessment, or PyLCIA. And I'll talk about how those modules interact to simulate circularity transitions in supply chains. So briefly, the discrete event simulation is how we capture material flows in the supply chain. The cost graph is how we store and use all of the information we care about, like costs and distances. And PyLCIA is how we calculate environmental impacts for the supply chain operation. More details to come in a couple of slides. Next slide. The CELAVI codebase is actually publicly available under an open source license. It's downloadable at the link that you see there on the slide, and we'll have that link a little bit later in the presentation as well. Actually, just yesterday, we made a new release of the codebase that includes some new uncertainty analysis capabilities, which we're pretty excited about. This is actually our second iteration of the code and model structure. We constructed this version of the model to be primarily data-driven, to reduce as much as we could the effort required to apply CELAVI to new supply chains. And so you can focus effort on data gathering and quality assurance rather than writing new Python code. The key input data sets for a CELAVI simulation are supply chain facilities, what kind of processes are involved, where they're located, renewable energy technology installations, or whichever technology you're interested in modeling, which in our case study, we're sourcing that from capacity projection data. You also need to know what are the constituent materials and the masses of those materials in the technology that you're modeling. And finally, you need life cycle inventory data, so material and energy inputs to the supply chain facilities and processes. Right now, our input data sets for the current case study that I'll talk about in a couple of slides are not publicly available, but if you're interested, please do reach out to Julian or myself, and we'll be happy to provide you with some of the data that we used and some templates if you're interested in getting started using CELAVI in your own case studies. Overall, a CELAVI simulation starts with data pre-processing and an instantiation of our three core modules I mentioned earlier: the discrete event simulation, cost graph, and the PyLCIA model. At the end of a model run, the output includes material flow histories, so those are time series, pathway cost histories, also time series, environmental impacts at a highly disaggregated spatial and temporal scale, and up to 2 default circularity metrics. And we've also recently implemented a new summary output file that includes fewer details, but kind of gathers all the really important stuff together. And that's to more easily explore variability across model runs as part of our uncertainty analysis. Not currently shown on this diagram because it's still in progress, is a visualization and decision support dashboard, which is going to be web browser based. And when it's complete, it'll be an interactive tool for visualizing CELAVI results and running some basic analyses, primarily for decision support purposes. So our idea is to create a product that we can show to decision makers and stakeholders for a case study, and have them kind of play around with the results and figure out what's actually going on, what CELAVI is telling them. So since that dashboard is still under development, we're only going to be showing a screenshot in the presentation today, but we're currently working on getting approvals to make that dashboard publicly accessible once it's complete, so stay tuned for more. Next up, I'm going to give even more information about our 3 core CELAVI modules, what they do, and how they interact. Next slide. All right, starting off with our discrete event simulation, or DES model. A discrete event simulation is a way of modeling a system as a set of processes, each of which is made up of individual events. We actually started off using system dynamics, or SD modeling, for material flows, which is what the DES captures. But we pretty quickly concluded that SD just doesn't provide us the level of resolution that we need for this type of simulation, particularly once we started incorporating spatial information and exact transportation distances into the model. The DES lets us model individual technology components, so not just a wind turbine, but a wind turbine blade, not just a solar panel, but a silicon wafer in the solar panel. And every component, as it's modeled in the DES, owns its constituent materials with masses. It owns an installation year, which we can get from capacity projection data, and it owns a useful lifetime that tells us when that component is going to enter end-of-life processing. And just as a side note, that useful lifetime can be modeled either as just a fixed value or can also be modeled as random draws from a probability distribution. So that it lets us explore scenarios around lifetime extension and how that can impact a circularity transition. So the events in the discrete event simulation are actually component transitions between steps in the supply chain. So from manufacturing to a power plant, from a power plant to an end-of-life processing facility, and so on. As all the technology components transition along the supply chain, we keep track of how many components are located at each facility over time, which tells us the supply chain structure and lets us calculate the supply chain environmental impacts. The most important event for a technology component is when it reaches end of life. And at that point, the DES queries another CELAVI module, the cost graph model, to determine which end of life pathway to implement for that component. I know this is another way that the really high resolution of the DES gives us an advantage because the preferred pathway can be different for components located at different power plants. And the pathway preference can also change over time as processing costs change. And we can capture all of that in our framework. Next slide. The cost graph model is how we represent all of the information we have about the supply chain superstructure, including what facilities are involved, how they're connected, where they're located, the processing steps at each facility and what those processing steps cost, the transportation distances, and the shipping costs between facilities. So we represent all of this information as a directed network, and that lets us perform calculations reasonably efficiently to compare various end-of-life pathways. And it also provides us a way to implement a decision-making process model that's behind determining which pathway gets implemented, where, and at what time. So by modeling the supply chain superstructure, which if you're unfamiliar with the term, it just means all of our supply chain options, linear and circular, we can avoid making any a priori decisions or assumptions about what pathways are going to be implemented. And instead, we can model pathway implementation over time as a consequence of supply chain characteristics like cost, transportation distance, and environmental impacts. Next slide. So the DES captures material flows, which are dependent on supply chain costs and other characteristics captured in cost graph. Our third module is PyLCIA, which takes the material flow information from the DES and calculates life cycle environmental impacts for the supply chain operation. Now we have here kind of at a high level what we're using in our data, data sources, especially our background inventory data. And we made these decisions because we wanted to keep all of CELAVI open source, as it is now. And that means keeping as much of the input data public as possible. So for this reason, we're using the US LCI database. We're adjusting that database using outputs from the Regional Energy Distribution System, or the REEDS model developed here at NREL. And that tells us how the electricity grid is going to evolve over time. And from all of that, we're calculating the Tracy 2.0 midpoint indicators. Because we have such a high level of resolution in the DES, we're actually able to calculate impacts for every individual facility and material, including transportation. So this lets us explore how the supply chain impacts change over time, hopefully with a circularity transition, and also lets us explore where these impacts are being generated and whether the supply chain is creating any impact hotspots as it's transitioning towards circularity. So this is critical information for circularity analyses because material circularity, supply chain circularity doesn't necessarily imply sustainability or even lower environmental impacts. So if implementing REACT's technologies and pathways means an overall increase in environmental impacts or a shift in where those impacts are located that could be harmful to some populations, we need to be able to quantify that trade-off in order to make better and more informed decisions about how we implement circularity transitions in the real world. Next slide. All right, so over the next few slides, I'm going to talk about our current case study, which we have one publication from last year in Frontiers in Sustainability, and we have an upcoming publication in Resources Conservation and Recycling, both on various iterations of this case study. So we're looking at wind turbine blade circularity in Iowa and Missouri. So we started working on this back in 2020. When there was a Bloomberg article that came out early that year about wind turbine blades at end of life kind of turning into an environmental problem. There were all these pictures of blades just piled up in a field somewhere, and it was made kind of a fuss here at NREL. So we decided to tackle wind turbine blades as our first CELAVI case study. primarily because, well, we know from the article they can be a problem. And we also know from a sustainability report that Vestas released in 2019 that about 85% of the materials in a wind turbine blade can be recycled, which an important distinction here is can be recycled, not are being recycled, just it is possible to recycle those materials. But the big exception, that missing 15%, is basically your wind turbine blades. So size requirements, the material used, and very, very strict strength requirements on new turbine blades all kind of interact to make end-of-life processing for blades pretty difficult. So what we decided to do is to kind of assess the end-of-life processes for blades that are closest to commercially and technologically viable, and then use CELAVI to model them to see if and how the blade supply chain might move towards circularity. So at that time, the two most viable processes that we could find were mechanical recycling through a company called Global Fiberglass Solutions and cement co-processing. So some nice news was that while we were initially writing the first iteration of this case study up, the news came out that Veolia, a turbine manufacturer, was actually partnering with GE to implement cement co-processing as an end-of-life option for their turbine blades. So that was a nice bit of real-world data validation for a case study. So what we're interested in using CELAVI to explore is under what circumstances, if any, does this blade supply chain transition towards circularity? What does that circular supply chain end up looking like? And what does the circularity transition do to the supply chain's environmental impacts? Next slide. So I'll be showing results for all three of the cost scenarios that we ran on three different levels of circularity cost, processing costs, but only one capacity expansion scenario, which is kind of the moderate case where we're assuming moderate advances in wind turbine technology and capacity additions over time. And we're also assuming no major changes to policies that affect the electricity grid mix. So in this slide, we're showing kind of overall what the supply chain structure ends up looking like over time, which is 2000 to 2050. And what we saw in this case study, kind of unusually, is that we're actually seeing circularity pathways implemented under all three of our circularity cost scenarios, low, medium, and high. And in particular, which I'm happy to talk more about if you have questions, we found that in this case, with the options that we had in our supply chain superstructure, the transportation costs wound up having relatively little effect on what pathways were implemented. So we actually saw the same pathways being implemented across our two-state region instead of seeing different pathways implemented based on location. However, some bad news is that we're never really avoiding blade landfilling, partly due to landfilling being a preferred pathway right at the beginning of the model run, where the circularity pathways still are pretty high in cost. And we also have our mechanical recycling pathway that involves some material losses, which do end up getting landfilled. So although we're seeing a circularity transition, we're not seeing anything like full or complete circularity. So in this graph, we're showing one of our two default circularity metrics, which is outflow circularity over time. And this metric measures the fraction of end-of-life material in the supply chain that is recirculated instead of being disposed of. And here we're not really distinguishing between closed loop or open loop circularity. Obviously, in this supply chain, there was no possibility of closed loop circularity. So here we're assuming that we're creating a material that can be used in a supply chain outside the wind turbine blades. So an outflow circularity of 0 means a fully linear supply chain. Everything becomes waste at end of life. And the closer the metric is to 1, the more circular the supply chain is growing. So a change in outflow circularity of time over time, of course, indicates a circularity transition. So for all three of our cost scenarios, we saw non-zero outflow circularity across the board, which is great. That implies that for this case study, processing costs aren't a major barrier to implementing some kind of circular pathway. Now, the different levels of outflow circularity that we're seeing are due to the different pathways being implemented. So the cement co-processing pathway, we couldn't find any information that indicated there were significant material losses in that pathway. So we're assuming no material losses. However, as I mentioned earlier, the mechanical recycling pathway does involve material losses. So while we're seeing circular pathways implemented in all three scenarios, we're not seeing the same level of outflow circularity. All right, so here we have a deeper dive into which pathways are producing environmental impacts and how those impacts are distributed both over time and spatially. So here, what we were looking for is, are we creating any impact hotspots, especially for environmental impacts where location is very important? For, say, global warming potential, we don't really need a nice heat map like this because we know, carbon generated anywhere is going to affect the atmosphere everywhere. But for, say, acidification, air impacts, we do want to know where those impacts are being generated. And here we're seeing under our high circularity cost scenario where we were implementing cement co-processing, we are actually generating a couple of impact hotspots, and those hotspots are where our cement plants are being located. So even though we have very high circularity, we are creating some impact hotspots. So that's an important trade-off to know about. Luckily, under our other two scenarios in which the mechanical recycling pathway was implemented, we're not seeing any hotspots. Which is primarily because the mechanical recycling facility, even though that's processing a ton of blade material, the only inputs to that facility really are electricity, is running grinding machines. That's pretty much all that's going on. We don't have any clinker production like we do in the cement co-processing, which is primarily what's driving those impact hotspots. So an important note is that we have drawn the system boundary for this study pretty narrowly. So we're not including any effects. We're not comparing cement produced from wind blade recycling to cement produced from all virgin materials. So if we were to do that comparison, we'd see that the cement we're producing actually has a slightly lower impacts than cement made from the traditional method. However, we drew the system boundary, as I said, just around this supply chain, and we haven't made that kind of consequential comparison just yet. All right, and last, but very much not least, this is the promised screenshot of our interactive visualization dashboard. And you can see here, we kind of have a summary of all the results that I've shown for our case study so far. And our vision is that we'll have all of the results from a particular case study loaded into this dashboard. And a decision maker can look at this, switch between scenarios, do some basic comparisons, maybe filter by high circularity or low circularity scenarios, maybe sort scenarios by in order of increasing environmental impacts, and do these kinds of basic analyses just to figure out what's going on in the system, what is the potential for circularity here, and what is the resulting environmental impacts. So again, we're working on making this dashboard publicly available. We hope to have it released sometime this fall if we can get approval for that. All right, so I'm going to wrap up our case study just with a summary of the lessons that we have learned. So we did calculate, as I mentioned, all of the Tracy 2.0 midpoint indicators. And when we did that, we saw that we do see an increase in global warming potential when circularity is implemented as compared to when we're just landfilling all the blades. And that's simply because there are extra processing steps involved in keeping that blade material in circulation. However, if you look at the whole blade supply chain, including manufacturing and that initial blade transportation step, the overall increase is pretty small. So even though we're increasing some impacts, the impact is relatively minimal. We did find that our environmental impacts from the circularity transition were pretty heavily variable spatially, temporally, and depending on which pathway was implemented. One kind of a wind blade specific finding that we found was that how the blades are reduced in size on site at the power plant right after the pull down off the turbine has a huge impact on which pathways are implemented. If your only option is blade segmenting, that is extremely expensive and your transportation costs go up by a couple orders of magnitude. So if you don't have the option to grind the blades on site to get that size reduction down, lower your transportation costs, you're going to have a very hard time seeing a circularity transition in this supply chain. So that's kind of a finding for future work out in the real world. How do we make that kind of technology readily available and cost competitive? And last but not least, this was a lesson that we learned, not really from our case study, but just as we were going along. We realized that even though we wanted to have some kind of circularity metric built into CELAVI, there is no one metric that works for all possible supply chains, all possible technologies, all re-X options. So we picked two that we think will work across a pretty wide variety of case studies, but we do want to emphasize that which circularity metrics are really going to be relevant and informative is going to depend on what exactly you're looking at, what your supply chain is, what your options are. So even though we have these metrics built in, we encourage you, if you'd like to use CELAVI in your own analyses, do some thinking about what circularity metrics really matter, and then work to implement those metrics instead of just sticking with the default. Next slide. All right, so as I mentioned right at the beginning of my section of the presentation, we've just completed a new release of the CELAVI code base that includes uncertainty analysis capabilities. So we're working on expanding the case study to include uncertainty analyses around what our input parameters are, especially around costs. We really want to know how sensitive are our results to variations in costs and other parameters like the material loss involved in the mechanical recycling pathway. Hopefully in future work, we're still waiting to hear if this project is going to continue or not, but what we'd like to do is include more REX options, more end-of-life technologies in our current case study, and start looking at additional case studies that have more options like waste to energy, like closed loop supply chain, like closed loop circularity, options like that. We want to test CELAVI's capabilities and make sure that it's really up to the task of modeling a general circularity transition. And thinking more long-term, we want to think about how do we increase the regional granularity, not just of what technologies are included, but what emissions and environmental impacts are being generated. So we know, say, a power plant, a coal power plant in Colorado, it's going to have slightly different emissions than, say, a coal power plant in the Southeast United States. And we'd really like to capture how those impacts vary spatially on site, not just at a life cycle level. And we're exploring options to incorporate more large-scale economic impacts as well into CELAVI. We kind of have costs that's not really an economic impact, but CELAVI as it is doesn't connect to a larger scale economic model, which will tell us the really fun stuff about like how are we generating jobs, what's our impact on GDP, all of those important economic metrics. So we're exploring ways to connect CELAVI to other larger scale models developed here at NREL, like the biome, which is a very long acronym at the bottom of the slide there. I'm not going to read it all out. But our hope is to use the CELAVI outputs as inputs to these larger scale models so we can run kind of a post-processing analysis and see what impact circularity transition has on these larger scale economic metrics. All right, and that is the end of my presentation. I'm going to pass it back to Julian.
Thank you, Rebecca. So another option that we are currently thinking about is to combine the CELAVI framework with the circular economy agent-based model that was also developed at NREL to improve the modeling of circular economy strategies adoption. So I'll just present quickly what is the CABM framework. That's an agent-based model that the aim of the model is to look at different technical, economic, and market conditions that would maximize value retention and minimize raw material input when applying different circular economy strategies. So we applied the framework to 3 different case studies that you can see here. Same as CELAVI, we also applied the model to wind turbines. And the model can look at different interventions or policies that could target different material efficiency potentials. So looking at intervention that are more technical interventions, some economic interventions, or market interventions that are aiming at changing behaviors of different stakeholders within the wind industry. So the model is representing 6 different types of agents: manufacturers, service providers, asset owners, recyclers, regulators, and landfills. It can also look at 4 different RX strategies: so redesign, reuse, repair, and recycle. So we can look, for instance, at the adoption of new designs from the manufacturers. In the case of wind blades, that can be the choice from the manufacturers to design thermoplastic resin-based wind blades rather than thermoset resin blade. We can also the model is simulating stakeholders' decision using a social psychology model, which is the theory of planned behavior that account for different factors that are affecting all those stakeholders' decisions. It is implemented in Python, same as for the CELAVI framework. The time step of the simulation is 1 year. So that's the temporal resolution of the simulation. And we are looking at the whole United States. So just to give an example of what are the type of different behavioral rules for our agent, we're looking here at the asset owner. So the asset owners is basically making two different types of decisions. The first one being to purchase a new versus a used or refurbished asset. So doing that, we can look at C strategies such as reuse of the asset. And the second decision that the asset owner is making is what to do at end of life with the asset. So what is going to be the end of life pathway that's going to be adopted from the different asset owners? Is it going to be repair, reuse, recycle, or is it going to be landfill? Or maybe the asset owner don't know what to do yet with the asset and is just going to store it somewhere. So that's the example of the Bloomberg article where all the landfill blades are just in the fields, waiting there on what to do with them. So we can also model this decision with the CEABM. And same as for the CELAVI framework, we're using a reboot function to generate the quantity of end-of-life asset at each time step. And we can actually represent all the different wind plant projects in the United States. So we use the United States wind turbine database to do so. We're able to get characteristics for the different wind plant project. So for instance, the size of the blades, the wind power capacity for the different wind turbines in the project, and things like that. So because states have different regulations regarding oversize and overweight road transportation that kind of hinder, that is a logistical hurdle to transport blades across states. And that's something that we were able to capture within the model that's going to actually hinder the adoption of recycling pathways, because you can see here on the map, we don't have recycling facilities in each state of the US. And so if we wanted to recycle, let's say some wind turbines blade from wind turbine in California, we would have to cross a certain number of states and make sure that we get all the size of the weight, road transportation permits and things like that. And like Rebecca mentioned, it's also very costly to transport those blades. That said, it's only if we want to transport those blades as big segments. Obviously, if we shred them on site before transporting them, we're going to lower the cost of transportation as well as ease the requirements in order to transport blades across state. And so that's kind of the result that we obtained here. We looked at a scenario with a really high landfill rate here because blades are transported as segment, and a scenario where wind plant owners are more inclined to transport, to adopt the recycling pathway because it's less costly and easier for them because they would shred the blade on site first. So if we summarize the two frameworks and the capabilities, we can see that they have some similarities. So they're both able to incorporate uncertainty. They are both spatially resolved, and they are both flexible enough to look at different technologies. And there are, however, some differences that makes it interesting to try to combine them to answer wider research questions and improve the analysis that we're doing with the different models. So regarding CELAVI, we can compute environmental impact, which the CEABM does not do. And we can also, there's also a neat results visualization tool that's incorporated directly in CELAVI, which the CEABM does not have as well. And the CEABM, however, can give us a detailed behavioral model for the different decisions that wind stakeholders may make regarding circularity. And it also accounts for the stakeholders' heterogeneity, being an agent-based model. So now what would be interesting is to combine those two models to answer some of the requirements from the Energy Act of 2020. So that's a piece of law that's been passed in the United States. And some of the language regarding wind recycling here are to minimize potential environmental impacts from recovery and disposal processes of wind energy technologies. and also to propose strategies to increase consumer acceptance and participation in recycling. Another interesting aspect of this Energy Act of 2020 is that it puts some emphasis on improving the recovery of critical materials. So typical critical materials for wind turbines are rare earth elements that are used in the permanent magnets of some wind turbines. So dysprosium, neodymium, and praseodymium. And so what we would like to do is combine the CELAVI framework in order to look at the different environmental impacts from the recovery and disposal processes. So answering one of the requirements of the Energy Act, and combine it with the CABM in order to capture the effect of having different intervention that could increase consumer participation in recycling. And for the emphasis on critical material, we could leverage a third project led by NREL, which is the Wind Material Property Database that kind of collect and organize a bunch of information on the different materials that are used in wind turbine technologies. And notably, the database also gives you information regarding the criticality of the different materials that are used there. So we could use those three different projects that are right now led at NREL and combine them to answer some of the questions from the Energy Act of 2020. In order to do that, we would probably extend the scope of CELAVI and the CABM to not only look at wind blades, but also look at the other parts, other components of the wind turbines, and especially probably focus on the permanent magnets that are used in drivetrains of some of those wind turbines. So that's all for us. Thank you very much. And if you have any questions.
Thank you both. That was so very interesting for our audience. And we do have some questions in the audience. And one of our analysts, Amos, will take the questions for you. Thank you.
Yeah, thank you, Holly. Thank you, Julian and Rebecca. Thank you for such an interesting presentation on circular economy LCA and visualization. You know, the transition towards a circular economy is such a timely issue, but despite its intuitive appeal, most of the benefits of circular economy are assumed rather than measured. So I'm really happy to see such kind of research ongoing in terms of developing useful and interactive frameworks to model and simulate circular economy outcomes for decision making. And good job to you guys, and all the best in your research. At this moment, I'm going to take some questions from the audience, and we already have a few questions from Danilo. Maybe Danilo, would you want to ask, or I can read the questions for you? The first question was your dashboard validated with the target audience? And related to that, what was the impact of this study results on policy and company decision making?
I can answer the first part of that question, which is a great point. Decision makers tend to be very picky about what kind of information they're presented with and how they use that information to actually make the decisions. So as of yet, we haven't validated the dashboard with our target audience. However, we have an upcoming meeting with our technical overview committee that's kind of guiding CELAVI and has provided some feedback all along. And we're going to run over the dashboard with them, kind of show them the capabilities, and then get feedback from that committee on how we should alter this dashboard. But I like this question because I'm actually on another project on how do you optimize research portfolios to maximize the impact of the next dollar of your R&D. And the two projects are more similar than you might think. And then the second question, the study To date, I don't think the studies had any kind of impact on policy or company decision-making. That's partly why we've been trying to shop CELAVI around and get this case study publicized as widely as possible, because we would love to talk to someone in the industry who is making these kinds of decisions and see if these results are informative, if they help support decisions, and if not, what else can we do so that we are truly making analyses that are valid in real-world decision-making processes.
Thank you, Julian. Do we have any questions from the audience? You guys can type in your questions, I'll read them out, or I'll allow you to speak. While we wait for the questions, how easily could the CELAVI model be applied to a different supply chain? Like, for instance, the electronics sector.
All right, so yes, that's, I love questions that let me brag about the CELAVI framework, because we did put a lot of effort really into making sure that this framework can be widely applied across different sectors, different supply chains. So of course, we're at the National Renewable Energy Laboratory, so we're gearing the framework and kind of how it's presented to renewable energy technology supply chains. But because the framework is almost entirely data-driven, we think it could be applied to different sectors, you know, the electronic sectors, maybe not plastics. Plastics is a whole nother can of worms. But the most of the effort that would be required to apply CELAVI to different types of supply chains would be in gathering the data. So not just what kind of technologies are entering end of life, but what processes are available to enable circularity in those supply chains. So I'm not saying it would be easy, but most of the effort would be in gathering data and doing data quality assurance rather than in rewriting a whole bunch of Python code.
So when we applied the circular economy agent-based model to the 3 different case studies, it's really a matter of collecting new data mostly, but there are a few changes that may be necessary. So for instance, there may be other circular economy strategies that you may think about, because obviously maybe electronics have like some reuse or repair options that wind turbine blade may not have. Or maybe the refurbish option is something that you really want to model. And so I think right now the CELAVI framework just look at recycling, but they may different recycling processes. But so you would have maybe to like incorporate new RX strategies as well.
And who was the creative person to come up with the name CELAVI, if I may ask?
So I think that's Annika Heberle, who was the project lead. I think she came with the name CELAVI, right?
It sounds nice.
I think, if I'm remembering correctly, it was actually another researcher here at NREL, Patrick Lammers, who was kind of our one on our internal advisory board. I think we were talking about, you know, combining the life cycle assessment and visualization and circular economy, and he just said, no, CELAVI. So it's been CELAVI ever since.
Nice. And Kelly has a question. What's the type of effort that is required to obtain the inputs to track the material flows? And how might it advise what metrics that are needed in those areas? And what are the recommendations when that data may not be readily available or possible to collect?
So I would say it depends a little bit. The type of effort required is going to depend a little bit on what type of supply chain you're looking at, because we focus more on renewable energy technologies, and because these tend to be, you know, utility scale or fairly large scale projects. There's a good number of databases on just how many wind turbines are there out there, how big are they, what's in them. Same thing for solar panels and for a few others. If you're looking at something that's a bit more diffuse and diverse like electronics, then it would probably take a lot more effort. Say if you were looking at laptop computers, you'd need to know, you know, how many are being manufactured, what are the constituent materials, and how much is in each computer. And then, you know, more information about like how long does each laptop stay in use. And then, of course, all of these circularity pathway options. I would say something that we found in general is there's just not a lot of information for these consumer product type things on what's out there, how much is being produced, where it's going, how it's being used, how long it's being used, what happens at the end of life. I guess that's a recommendation that there could be more study in that area. But before that, I think there needs to be a real value add on that kind of data. And until now, we haven't really needed to use that for anything. But as circular economy analyses and the circular economy in general gain ground, I think we'll see more pressure to develop the kinds of databases that we see for larger technologies so that we can really track all the materials that are in consumer products as well. And then for your second question about focusing on a specific material, zooming out to assembly, looking at a larger complex product, that's exactly what CELAVI is designed to do, actually. Using our discrete event simulation, we can model materials in technology components. So in our case, we had wind turbine blades. There's two things in a wind turbine blade, really. There's glass fiber and then there's epoxy. So we're modeling both of those. But if we were to model, say, a solar panel, then we would be able to capture not only the whole solar panel and everything that's included in it as it sits in a field, but we could individually track the glass in it, the silicon wafers, the different kinds of metals, the aluminum frame, the plastic housing, all that kind of thing. So that is there. It does take more effort to gather that data. And then, of course, the more complexity and the more resolution you have in the data, the longer the model takes to run just because of the sheer number of events happening in the discrete event simulation. But it's certainly possible to have that kind of resolution and look at individual materials, technology components, and entire technology units.
Thank you. We have an additional question from Danilo. Maybe Danilo, are you able to speak? I think I promoted you to speak. If not, you can speak.
I almost, yes. Thank you.
Okay, go ahead.
Thanks for the word, and thanks for the great presentation, the great work, the framework you both produced. I'm Danilo from Chile, and well, I think my first question was already answered. You mentioned it takes a long time to evaluate. So my first question was if it's possible for the end user of a dashboard, for example, to create new scenarios based on a slight variation of an underlying parameter. And secondly, how long does it take for a typical run to process a scenario?
All great questions. I'm loving these. So through our visualization dashboard, our intent is not really to run new scenarios through the dashboard, but just to gather related scenarios results together for exploration. However, in our this code base release that we just completed yesterday, we have added a capability where in the part of the input data sets, you can actually specify a list of values that you want to explore for a particular parameter. So for instance, instead of saying, landfilling costs $10 in 2020, you could say, well, what happens if it's $5, $10, $20, $50? And then CELAVI will automatically execute 4 times on each of those parameter values. So we have that kind of implemented throughout our input data set now. So it would take a little more legwork, and we don't have like a nice web browser tool for it yet, but that is definitely possible in our release that just came out yesterday. And then, and then how long does a typical simulation take to run? So we do testing of the CELAVI code base on just our personal our NREL laptops, so just our local machines. And there for our Iowa, Missouri case study, which is, I want to say around 1,000 facilities and 50 years worth, it takes about an hour to run one model run. However, we've been taking advantage of NREL's Eagle supercomputer to execute our uncertainty runs and do runs also in parallel. And there, I don't know if I know the exact number off the top of my head, but for one run and with a few fancy specifications that speed up the life cycle calculations, which are really one of the slower parts, there I think we can get through a full 50-year Iowa, Missouri run in, I want to say 15 to 20 minutes. So from an hour to minutes. And then what we've been finding is that that stays pretty consistent. But of course, as you add in more facilities, more power plants, more wind turbine blades, that simulation time does lengthen.
Thank you, Rebecca. Do we still have any more questions? If not, I guess I'll just go ahead and ask you about the wind blade case study, where you found out that the transportation costs were not a major factor in the circularity transition. And this is quite unusual for circularity analysis. And can you explain why the transportation costs were not so significant in this particular case study? And are you also confident with these outcomes?
That was honestly one of the more surprising findings out of this case study. I mean, we were expecting transportation costs to be like one of the main deciding factors. And, when we were developing CELAVI, we talked to people, in the wind industry and construction, and they were all saying it costs so much to transport this very low value material. And that's why no one wants to do anything with it except ship it to the nearest landfill. So the reason in our case study why we found transportation costs weren't significant is because we included the option to do that more extensive blade size reduction on site at the power plants. So what that would look like is some kind of mobile grinding equipment would be shipped out to the power plant that's being decommissioned. All the blades would be shredded into very fine material. And then the shipping costs for that are at least an order of magnitude below the transportation costs for an entire blade or even a blade segment, which are both very, very difficult to transport. If you've ever seen one going down the highway, they're enormous. They're very hard to get anywhere. So what I think is happening is there are probably some costs there that are being obscured by our input data, especially the cost of doing that size reduction on site at the power plant. When we were kind of scoping out that mechanical recycling pathway, we were talking to people in industry who were saying, oh yeah, you can just grind the blades on site, no problem. We think that was probably a little overly confident, maybe a little overly optimistic, but that kind of brought us to another knowledge gap that maybe hasn't been explored as thoroughly in the circular economy space. And that is, if we're talking about all of these technologies that look great on paper and could be really beneficial, what's it actually going to take to get those technologies deployed at scale in the real world? So I think practically what we would see in the real world is that on-site coarse grinding might be cost prohibitive, might be much more expensive than we're assuming it to be. So in that case, segmenting might be more expensive, or landfilling might just be the optimal pathway, speaking economically. However, that's something that we're going to explore just to build a little more confidence in our results with our uncertainty analysis capabilities. We're going to be looking very closely at the cost of that on-site size reduction and seeing how much can that cost vary before our results change. So we'll end up with a range of, as long as you can do the on-site blade grinding, below X dollars per metric ton, then these results are valid. If it's more than that, we're going to have to rethink our results. So we're still kind of exploring that, but we're definitely looking into it.
Yeah, interesting.
I would add to the discussion that very often when we look at transition and we do our models and everything, we very often that all of those transitions are really constrained by the infrastructure. And so in the case of wind blade circularity, the constraint is having a shredder, a mobile shredder. Even if it's not too expensive, you still need to have one somewhere that you can rent or buy or purchase, and then bring it all the way to your wind plant project. So same thing with offshore wind. If you want to install turbines offshore, you need special boats, special barge, and those are there are limited numbers of those around the world, and they can only be at one site at a time, and so that's also going to constrain your development of offshore wind. So we need to incorporate more of those aspects into our modeling, which we're trying to do here at NREL.
Thanks, Julian. Rebecca, you mentioned about grinding. Do you foresee any mobile grinding industry or services being born out of this research or otherwise?
That's the hope. At this stage, I have to say, I don't know. I would love to see that. We're probably going to try and follow up with some of the people that we talked to at the very beginning of this case study development to kind of revisit our results with them and run it past them just to see if it passes their own personal sniff test. I would love to see these results go out to, Veolia, say, or GE, and have them say, oh, okay, here are the needs for technology deployment, and further development. I don't know if that's going to happen, but we're going to do our best.
Thank you. Just one last question, and this is more on methodological integration. I was recently working on a project where we were promoting the integration of models, of methods for analyzing circularity, because just depending on one method, you may come out with, misleading outcomes, or we become more, narrow-minded. What is your opinion in terms of methodological integration, like LCA with other methods, and what are some of the challenges that you have faced in trying to integrate these different methods? Because integration can occur at different stages. Some of it can be at database level, some of it can just be at the results interpretation level. So my question is just like, what some of the challenges that you have faced in trying to integrate methods?
Yeah, that's a really good question. And I think, so first of all, it's going to take you more time than if you just, obviously, if you're trying to combine two different methods, it's going to take you more time than just applying one.
Yeah.
I would say that the biggest challenge is to make sure that the assumptions, the underlying assumptions of your methodologies are the same.
Yeah.
So the assumptions are very often depending on the model you're trying to build. So you kind of have some flexibility there, but whenever you combine two models, you need to be sure that the temporal scope is the same, the geographical scope is the same. You need to make sure you're not double counting anything somewhere.
Yeah.
So you need to align the underlying assumptions of your methodologies. And the other point I wanted to make is that it's also it's not always beneficial to try to integrate two different methodologies. It depends on the research question.
Yeah.
So I think the first step is really to think what you're trying to do and what you need to do that. So the little exercise that we showed at the beginning of the presentation, I think it's a very helpful exercise to try to list all different type of methodology, what they can do. Mm-hmm. And that's pretty subjective. So, it's going to depend on how familiar you are with a certain methodology. Somebody who's really, who knows really well life cycle assessment will say, there's no problem, uncertainty is really easy, I can do that. But somebody that maybe is not as familiar with LCA will probably start with a simple LCA model that does not account for uncertainty. So you need to list all of those capabilities of your different methodologies as you understand them, and then look at what you're trying to do and see what the tools that you can use there.
Thank you.
Well, thank you all so much, Rebecca, Julian, Amos. Very happy to have you all here, and it was a wonderful webinar. And thank you. We can make this available to everybody on YouTube. Until next time, thank you. Bye-bye.
Thank you. Bye.